Good morning, everyone. My name is James Clark, and I'm a senior studying chemical and biomolecular engineering at Johns Hopkins University. I'm an ORISE fellow at NETL Pittsburgh, working with Dr. Nicholas Seifert on water management. And today I will be presenting my work on simulating material fluxes and osmotic processes using species chemical potentials. I want to start by putting my work into context over here. NETL has been working on alternatives to disposal wells for produced water management for quite some time, and Figure 1 depicts a proposed treatment plant that extracts valuable raw materials from produced water. But produced water, being in the 150 plus gram per liter TDS range, is far too concentrated to be treated using membranes currently. That's where osmotically assisted reverse osmosis comes in to solve that problem. OARO can lower the effective osmotic pressure of high TDS brines by sweeping a low TDS saline solution across the permeate side of the membrane. This allows further concentration in a series of steps using membranes, as shown in Figure 2, to produce fresh water and ideally valuable chemical feedstocks such as 10-pound brine, minimizing waste as shown in Figure 1. OARO is notably cheaper energetically than using thermal distillation process for this task, but membrane separation textbooks and current theory were not developed with produced water levels of salt in mind. So my mentor and I wanted to go back to first principles to model OARO fluxes. So as you're probably aware, we're going to be talking about modeling variations of reverse osmosis, or RO, today. Briefly, RO separates salt from water by forcing water to diffuse through a semi-permeable membrane, overcoming the osmotic pressure resistance with applied hydraulic pressure. These processes are often described in textbooks using equations 1 and 2. The first equation defines volumetric water flux JW through the membrane as a linear function of delta P minus delta pi, or the difference between hydraulic and osmotic pressure. The second equation defines molar salt flux JS as a linear function of concentration gradient delta C. And understanding this traditional flux model has been the focus of my work at NETL this year. I found that currently A and B are fit knowingly or not as constants in a sort of black box model shown here, but the parameters inside of it are rarely mentioned. So there are a lot of assumptions that must be considered on a case-by-case basis, ideally. Another challenge to membrane flux modeling is that the osmotic pressure and concentration gradients across the membrane require interface concentrations in order to be modeled correctly. So in Figure 3 below, we see that the interfacial concentrations are not equal to that of the bulk solution that we know, as you can see. And concentration polarization, or CP, can have a dramatic effect on fluxes. So this is important to model, but it's beyond the scope of my work, and I accounted for it using equations 5 and 6. And so thinking back at the assumptions involved in equations 1 and 2, I spent a lot of time during the fall reading about the origins of the JW and JS equations, which led me to irreversible thermodynamics, or IT, as the basis for membrane separation theory. IT shows up in the literature today as the minimum energy of separation calculation, which is shown in equation 7. This equation may look insignificant, but it contains non-ideal thermodynamics, and it's what led me to look into IT in the first place. And what I found is that although the flux equations that use A and B hardly look like thermo, they are definitely derived from it. So when I looked further in the literature, the origins of the flux equations were, again, knowingly or not, derived from Onsager's hypothesis, which is a generalization of the experimental flux equations such as Fick's law of diffusion, Newton's law of viscosity, Fourier's law of heat conduction, generalizing a driving force to a flux using a phenomenological coefficient. So for going a lot of the math, equation 8 can be substituted with a chemical potential gradient as the driving force to become equation 9, which can then be used to calculate JW and JS as we integrate across the membrane as shown in Figure 10. So this led my mentor and I to pursue the Gibbs model as a sort of generalized flux equation for reverse osmosis processes. I call it the Gibbs model because chemical potential is synonymous with partial molar Gibbs free energy, and it rolls off the tongue a bit better. The Gibbs model should be able to calculate the membrane water and salt fluxes as long as we can calculate the activities and partial molar volumes required to use equation 11 to get chemical potential in the first place, which is no easy feat. So that's why the equations are generally simplified. So now I briefly want to go over the data collection process, which I was not involved with. In 2017 and 2018, my predecessors were motivated by much the same goal of improving membrane flux modeling, with Jacob Weidman and Jason Arena experimentally measuring OARO, RO, and PRO fluxes in a bench scale experimental setup shown below in Figure 4. I used the data sets from these experiments to test my Gibbs model. My original task was to go beyond the traditional flux equations in order to understand the assumptions behind A and B, because especially for OARO, they might not apply anymore. Along the way, I intended to find out, does the Gibbs model work? Does it work better than the traditional equations? And is it even worth all the trouble using the following data analysis? So first, I went to a software I am familiar with for aqueous chemistry, Olali Studio. I surveyed their thermodynamic model to fit partial molar volumes and activity coefficients required in the chemical potential equation as functions of concentration. I fit the parameters of the Gibbs model and the traditional model by minimizing the sum of reduced chi-squared residuals, as shown in equation 14, which yielded the best fitting parameters to the model, to the data, and goodness of fit measurement, chi-squared over n, the chi-squared test statistic. Excel's nonlinear optimization toolkit worked wonders for this task. And once the parameters were fit, the models could be compared using the experimental data, which is how I will show my results over here. So first, we have 4 plots here. And this case is when all 200 data points for OARO, RO, and PRO were modeled using the same 3 constants, A, P, and S. To give you some bearings here, I compared results of fitting the traditional flux model from the beginning on the left and the Gibbs model on the right to the experimental data. So the x-axis is the predicted values of the flux, and the y-axis is the experimental measured values. The top 2 plots are water flux, and the bottom 2 plots are salt flux. The fit minimized the error. So ideally, the model data shown on the x-axis would accurately model the experimental data shown on the y-axis, and this would collapse perfectly onto the y equals x line. But although this is a good fit, it's not perfect, and the chi-squared and chi-squared over n are provided. And as you can see, the Gibbs model is certainly on par, as you can see with the goodness of fit parameters, with the traditional model. And this answers the first of my questions. The Gibbs model definitely works. So moving on to figure 6, we look at a 13 parameter model in the same setup. And although the goal is to ultimately model RO, PRO, and ORO using a single model, single set of parameters, like shown in figure 5, the 2 sets of parameters summing to 13 minimize the error much more. Additionally, in this fit, A and B were modeled as functions of concentration and S as a function of pressure. And this led to the fits being notably tighter than what we saw in figure 5. And this is reflected in the chi-squared and chi-squared over n being much smaller. And this provides evidence that the memory parameters are certainly not constants, showing that the Gibbs model could be better for OARO cases and salt flux. Now, where does this research leave us? Well, first, now we understand the fundamental theory behind the A and B parameters, and we can choose whether or not to include their assumptions on a case-by-case basis, depending on the application. And second, we realized that because of thermodynamic modeling software such as OLI systems, we can use a more advanced flux equation now that takes into account more driving forces in a straightforward, more fundamental form that resembles Fick's law. And it may no longer be necessary to simplify chemical potential into delta P minus delta pi anymore, but that remains to be seen. And this model fits material fluxes better than the traditional model, and it's definitely worth further investigation, especially for high salinity processes that we're concerned with. And thus, the A and B parameters are not best fit as constants, especially for those high salinity processes. And by varying our data fitting methods, we can explore their dependence on different variables. And with that, I would like to thank ORISE and NETL for sponsoring my participation in this research, Jake Wyman and Jason Arena for their experimental data, and of course, my mentor, Dr. Nicholas Seifert, for his guidance during this process. Thank you for listening. And now I would love to take any questions from the audience.